In today's video, we're going to be discussing perpendicular bisectors within triangles. So in chapter 1, you learned that a perpendicular bisector intersects a line segment at its midpoint and is perpendicular. So these hash marks indicate that that is the middle, that D is the middle, and then this indicates that the ray, line, or segment here is perpendicular to segment AB. So we get a perpendicular bisector. The perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment that was being bisected. So for this example, point C is on the perpendicular bisector. That means that the distance from C to A is the same as the distance from C to B. Likewise, point D is also on the perpendicular bisector, and we already know that because D is the midpoint as well, that it's the same distance from A as it is to B. But any point on this perpendicular bisector, let's say I was here and I called it point E, E would be the same distance from A as it is from B. The converse of that is that if a point is equidistant from both endpoints of a segment, so let's say here's a segment, and I told you that this point was the same distance from R as it was S, then I know that this is on the perpendicular bisector. That's what the converse is stating. Okay, so that's really just an isosceles triangle when you look at it that way. All right, let's apply those two theorems here. I see the hash marks. That means that X is in the middle. I see the right angle box, which means this is a perpendicular bisector. W is a point on that perpendicular bisector, and these are the endpoints of the segment that's being bisected. That means that this is the same as that. So now we can just do 2x plus 11 equals 4x minus 5. We solve this by subtracting 2x. 11 equals 2x minus 5. Add. Divide. We get x equals 8. X equals 8. They also say find the length of each segment. Well, I have to assume that they mean WZ and WY. And we know that WZ and WY are the same length. So I'm going to plug in 8 to one of these, and I will find the length of both. 2 times 8 is 16, plus 11 more is 27. And that should be the same for both. In example 2, line OQ is the perpendicular bisector of MP. Well, let's look at the diagram. That first tells me that O is the middle of MP. So this is the same length as this. Q is a point on the perpendicular bisector, which means it will also be the same distance from Q to M as it is Q to P. And lastly, they already identified these as both being 15. What does that say about point L? Well, if L is equidistant from the endpoints of segment MP, then L is on the perpendicular bisector of MP. Which segments are equal? Should say which segments are congruent, but that's okay. We know that MQ is the distance of MQ is the same as the distance of QP. We know that MO is the same as OP. And we know that ML is the same as LP. Find X. All right, so for part B, I'll go down here. X is this expression, is in that expression. And that expression should be equal to that expression. So 4x plus 3 equals 11. 4x, after we subtract that, would be 8. X would be 2. X is 2. Is L on line OQ? How do you know? C. Yes, we already talked about this. L is equidistant. From the endpoints of segment MP. Thus, making it a point on perpendicular bisector OQ. Because this is the same distance as that, then if I extended this, it's going to have to run through point L. Now let's talk about a point of concurrency. Point of concurrency is when 3 or more lines intersect at the same point. Now let's look at this triangle, and we're going to use perpendicular bisectors. What is true about every point on the perpendicular bisector of segment AB? So think of this as just a segment, not a side of a triangle right now. If I drew the perpendicular bisector, let's use my tools here. If I drew a perpendicular bisector, I'm guessing, I don't know where the middle is right now. There's a way to find it. There's a good way to find it, but that looks pretty perpendicular. Now finding the middle. What is true about every point on this segment that I just drew? The answer to that should be every point on the perpendicular. They are equidistant from points A and B. What is true about every point on the perpendicular bisector of BC? Okay, we're going to try to find the middle. I'm trying to make it perpendicular. I know I'm not in the middle right now. Start with perpendicular, then I have the ability to move this. If you're doing this on your own, to keep things simple, you would use a ruler to find the middle. Okay, so what is true about every point there? they are equidistant from points B and C. So if every point on the red line is equidistant from A and B, and every point on the orange line is equidistant from B and C, what would be true about that one? Think about that. Let's move forward here. What is true about every point on the perpendicular bisector of AC? Okay, we're going to find the middle of AC, and we're going to draw a line that's perpendicular. That's my best bet. And we're going to move it to where we think the middle is, and that's pretty close. And since that's where I'm going to make it, they are equidistant from points A and C. So again, what is true about this point right here? First of all, that's a point of concurrency because three lines intersect at that one spot. But we know that because it's on the red line, that this distance here is the same as this distance here. And we know because the orange line that this distance here is the same as this distance here. Shouldn't that point be equidistant from what we call the vertices of the triangle? Point D is equidistant from the vertices of the triangle. So point D is equidistant. So AD, BD, and CD are all the same length. Now, we can test this to see if that's true. See if I did it right, actually. And it will be true, but I'm not perfect on this because otherwise, when I drew that circle, it would have hit all three vertices at the same time. I can adjust this a little bit, I think. It would have been closer to here had I actually found the perpendicular bisectors correctly. But that's what doing the perpendicular bisectors, finding the perpendicular or the point of concurrency for the perpendicular bisectors does. So the circumcenter, what we found was the circumcenter. That's the point of concurrency for the perpendicular bisectors of the sides of a triangle. The circumcenter is the center of a circle that passes through all the vertices of a triangle. We say this circle circumscribes the triangle. This means the circumcenter is equidistant to the vertices. And that's what we're going to note from that, is that the circumcenter of a triangle is equidistant from the vertices of a triangle. So in this diagram, PC is a perpendicular bisector, QC is a perpendicular bisector, and RC is a perpendicular bisector. They all meet at one spot called point C, and that means that L to C, so from here to here, C to M, and O to C are all the same distance because of that. Here we are told that point D is the circumcenter of the triangle. And they're telling me then, because they say that it's a circumcenter, they're telling me that this is the same length as this is the same length as that. They give you an expression for DB and AD, and we know that they're the same length. So we can say DB is equal to AD, and we can plug in those expressions and solve. Subtract the x to get 2x minus 7 equals 25. Add the 7 to get 2x equals 32. Divide by 2 to find that x is 16. So anytime they're telling you about a circumcenter, you know that it's equidistant from the vertices, and you can use that to answer questions. That concludes our lesson for today. Thank you.